Okay guys, this week's experiment is called Density of Liquids and Solids. You'll have to fill out a report sheet, quite a few pages from page 27 to page 36 here. Now, whoever put this experiment together on the Blackboard site, on the CNM Learn site, they made some modifications. So it's a little bit confusing. Now, what I've done is I've gone and made modifications to the report sheets. I'll be going through these, showing you how to fill them out, and hopefully it'll make it a whole lot simpler for you. But before we talk about the report, let's talk about density calculations in general. You got to get pretty good with density. It's an easy one. Density, I'm sure you've been told in lecture by now, density is defined as the mass of something divided by its volume, how much space it occupies. That tells you the density of something. So if you want to find the density of a particular substance, you got to make two measurements. You got to measure how much does it weigh. You got to measure how much space does it occupy. What is its volume? Simple example here. Say you have a 5 milliliter sample of concentrated sulfuric acid. That's H2SO4. You might not know that's sulfuric acid yet, but that's the formula for it. That's what you know and love as battery acid. So your car battery is filled with this stuff. So you have a 5 milliliter sample of that. That 5 milliliters represents the volume. You weigh it, you find it weighs 8.95 grams. What's its density? Oh, the density is the mass over the volume. So your 8.95 grams, 5.00 milliliters. You do the math on this. 8.95 divided by 5. You're going to find it's 1.79. So your answer is going to be 1.79 grams per milliliter. Now, just so you know, you can write this answer this way. You'll sometimes see it written this way: 1.79 grams milliliters to the -1 power. Don't let that bug you. You've got to get used to this in the sciences. Sometimes we use negative powers on units. If you see a unit raised to a negative power, it simply means that this whole thing is a fraction, and the thing raised to the negative power lives on the bottom. So this is absolutely the same as this, or the same as saying 1.79 grams per milliliter. The word per, when you see the word per in the sciences, it means it's a fraction. That's the word per right there, is that fraction line. 1.79 grams per milliliter. You'll see it typed up as 1.79 grams / milliliter. Same thing. So all of these mean the exact same thing. Okay, so that's finding the density of something. Another big concept with density is density can be used as a conversion factor. Now, density, of course, is mass over volume. This is an algebraic expression with 3 terms. If you know 2 of them, you can find the third one. So if you happen to know the density of something, you know how much it weighs, you know its mass, you could solve for the volume. Or if you happen to know the density and the volume, you can solve for the mass. It's just a little bit of algebra. Now, algebra is great stuff, but you can work most density conversions without doing any algebra at all. So let me show you an example here. Let's say you happen to need 12 grams of sulfuric acid. You need this. You need 12 grams of the stuff. You know that its density is 1.79 grams per milliliter. How many milliliters do you need? Well, if you recognize that this is a conversion factor, this means 1.79 grams per milliliter. You can work this as a conversion factor problem. If you start the problem with 12 grams, that's what you need, 12.0 grams, and you set it up using this as your conversion factor. You set it up so that the units cancel, you'll be good. So I would take this thing, and I wouldn't use it the way it's written. I'm going to take this and I'm going to flip it upside down when I put it in here. So it's going to be 1 milliliter for every 1.79 grams. Do you see how the units of grams cancel? Any unit that is on the top of one thing and the bottom of another gets canceled. The only unit that did not get canceled is the milliliters. So we'd get 12 divided by 1.79. We'll get 6.70. So if you needed 12 grams of sulfuric acid, you would need that many milliliters. In quite a few places in this report sheet, it's giving you problems where you know two of those terms. You know the density and the mass, or you know the density and the volume. You're solving for the third term. You can do it this way as a conversion factor. If you had to, you could work it algebraically. This same problem, if we had to do it with algebra, you could say, okay, I need 12 grams of it, that's the mass. I have the density 1.7, so I have the mass, I have the density, I have to solve it for volume. You would say, okay, I'll multiply both sides of this equation by volume, and you'll end up with density times volume is equal to mass. And then you'll divide both sides of this equation by density, and you get volume is mass over density. Plug in your stuff, 12.0 grams all over 1.79 grams milliliters to the negative 1. Guess what? You get the same darn answer we got below, 6.70. Oops. Milliliters. So again, you can do the algebra, or you can just recognize that this is a conversion factor. You can use it the way it's written, or you can flip it upside down like I did. You flip it in such a way that the units you don't want get canceled out. Doesn't matter which method you use. Algebra is good stuff. Conversion factors are good things. But quite a few problems in this lab where you have two of these variables and you got to find the third one. Okay, now let's get down to it here. When you're filling out your lab report, you have to do the pre-lab, kind of scan everything in all together, the pre-lab, the lab report, the post-lab, scan it all in as one PDF and submit it to me. This first page is just going through how to read things correctly. We had a earlier discussion on how many decimal places you read stuff to. So if you're looking at this graduated cylinder, this is 5 milliliters, this is 6, so this is 5.1, 5.2, 6.1, 6.2, 6.3. So this graduated cylinder is marked in tenths. If it's marked in tenths, you read it to the nearest hundredth, or 2 decimal places. The graduated cylinder pictured below, you take a look at it. This is 50, 51, 52, 53. It's marked in the ones place. So if it's marked in the ones, you read it to the nearest 1/10. Question number 2 here on page 28, you can skip that one. That one didn't make much sense to me. The other problems here are pretty simple density problem. Last part of this thing, they have a problem here. This is the more interesting part of this lab, where you're not measuring density, but instead you're using density to determine the thickness of a piece of aluminum foil. Just refer to the PDF that they gave you. You'll be able to see the length, the width of the aluminum foil, the mass. If you're wondering how to work this type of problem, there's a sample problem for you that's very, very similar I've set up. And what you're doing in this process is you're making an indirect measurement. That's something we do in the sciences all the time. We make indirect measurements. So pretend this is your foil. It's not, it's paper. But if you wanted to measure how thick the paper is, well, darn, you can't do that directly. You can't put a ruler here and measure the thickness. But you can measure how long it is. You can measure how wide it is. You can weigh that piece of paper. I weighed it. It weighs 0.150 grams. If I happen to know the density of the paper is 0.709 grams per cubic centimeter, so that's 0.70 grams per cubic centimeter. That's the density. Now, to find the thickness, it's a two-step process. First, you're going to use the mass and the density. We know the mass. We know the density. You're going to find the volume. How much space does this piece of paper take up? It doesn't occupy much volume, but it's real. It exists. It does occupy some space. So how do you do that? Again, I do conversion factors. So I would say, let's see, it weighs 0.150 grams. I would take this guy here, my density, and say, oh yeah, I got 1 cubic centimeter for every 0.70 grams. And 0.15 divided by 0.7. I'm going to get 0.21. 0.21 cubic centimeters. That's the volume of this piece of paper. That's how much space this thing's taken up in cubic centimeters. Now, what I'm after, of course, is the thickness, right? I want to know how thick it is. So I've kind of drawn a picture of the paper here. There's the length. There's the width. And what I want is this thickness. It's not as thick as I drew it here. It's paper thin. Forgive the pun. But I know that the volume of a rectangle is given by the length times the width times the thickness. So the volume of that piece of paper, the volume, well, I know that volume. It's 0.21 centimeters. 0.21 cubic centimeters. I misspoke. That's the volume of the paper. And that's equal to this length, 12.70 centimeters. Times this width, 7.62 centimeters. Times this thickness, K. I've got an algebraic expression here for the volume. I know this number, this number, this number. All I have to do is solve it for the thickness. So if you did that, if you solved that guy for the thickness, 0.21 divided by 12.7 divided by 7.62, you would find it's 0.0022. 0.0022 centimeters. That would be how thick the piece of paper is. Again, that's an example of an indirect measurement. We do that in the sciences all the time. There's something you can't measure directly, but you can make some other measurements and you can figure out what you're after. Now, so you're going to do the same type of calculation for your aluminum foil here. Same exact type of calculation for your aluminum foil. The rest of this, the post-lab, pretty straightforward stuff. This first problem here, they're telling you you have this many milliliters of liquid water. It gives you the density of that liquid water. Hey, you got the volume, you've got the density, you're going to solve for the mass. And then in the next part, you'll take that mass, you'll have this mass with this density, you're going to solve for the volume. It's easy, you'll see when you start doing it. Pretty simple stuff here. One problem that comes up here at the very end of this lab report is talking about a perfect cube of jade with this mass and this density. You know what to do. You've got the mass, you've got the density, you're going to solve for the volume. That's half the problem, solving for the volume. But what it's asking you is, what's the edge length of the cube? So you have to realize it's a cube, and I'm sorry, I don't think I can draw a very good cube. I will try my best. There's my cube. Hey, the edge length is the same everywhere. It's a perfect cube. So if you happen to know the volume, you know how many cubic centimeters of space it takes up, and you want to know the length of one edge, take the cube root. I always get people that do this lab report, they get the volume and then they divide by 3. No, don't divide by 3. Take the third root. Now, if you're wondering, how do I take a cube root? I'll show you on a couple of different calculators. Here's my favorite calculator. Let's zoom in on it. And a little heads up here. You have some math functions that you're not familiar with on a calculator. Make up a problem that you know the answer to. For instance, for this one, I would say, hey, the cube root of 8. I know what that is. The cube root of 8 is 2. Because 2 times 2 times 2 is equal to 8. So let's see if I can get my calculator to do that. On this particular model, I don't have a cube root button, but I do have, where is it? Right here, right above the y to the x, I have a button that allows me to take any root I want. So to see if it's working right, I would say I'll put in 8. I'll say boom, boom, so I'm accessing that guy. Now I want to take the cube root, so I push a 3. It gives me the cube root of 8. So again, on this one I would put in the number I want to take the cube root of. I access that weird radical feature. I say take the third root of it, and it gives me the right answer. So I know that's the way to do a cube root on this calculator. If I hadn't gotten 2, I would play around with things until I get the right answer, and then I know I'm doing it right. Now, a very popular model here is this calculator. A lot of you, I imagine, have this calculator. It's one of the more popular models out there. Taking a cube root on this one's a little bit different. Now, the button you want is this guy. Do you see how he's got that little radical sign with an X? So for this one, you don't put in the number you want to take the cube root of. You say, first you turn it on. You say 3, because I want to take the cube root. And then you say radical of 8. So that's telling it to take the cube root of 8, and you get 2. So when you get to this part where you have to take the cube root, you're not going to be taking the root of 8, you're going to be taking the cube root of whatever that volume is. But that's how you do a cube root on those two calculators. Other ways you can do it, you might recall from algebra, anything raised to the 1/3 power is the same thing as taking the cube root of that thing. So check it out here. If I had 8 and I raise it to the 1/3 power, so I go y to the x, 0.33333333, 0.3 is 1/3. Boom. I get pretty darn close, right? Anyway, hope that helps with how to fill out this lab report, and I will get this video up soon.